Okay, now we're going to talk a little bit about the net change theorem. The fundamental theorem of calculus states that if f is continuous on a closed interval a to b and f is an antiderivative of f on a to b, then the definite integral from a to b of little f of x dx is equal to capital F of b minus capital F of a. But because capital F prime equals f of x, this statement can be rewritten as the definite integral from a to b of capital F prime of x dx is equal to capital F of b minus capital F of a, where the quantity capital F of b minus capital F of a represents the net change of f on the interval a to b. So what's all that mean? Well, that's the net change theorem. So the definite integral of the rate of change of the quantity f prime gives the total change or net change in that quantity over the interval. So let's just think about this. A chemical flows into a storage tank at a rate of 180 plus 3t, liters per minute at time t in minutes, where t is between 0 and 60. Find the amount of chemical that flows into the tank during the first 120 minutes. So what you do is let C of t be the amount of chemical in the tank. Then C prime represents the rate at which the chemical flows into the tank. So if I integrate C prime of t from 0 to 20, that's just like integrating the rate, so 180 plus 3t. Anti-differentiate, plug in 20 and 0. So we get 300 plus 600 minus 0 plus 0, which equals 4,200. So this is kind of like C of 20 minus C of 0. Okay, it's 4,200. So what that means is that the amount that flows into the tank during the first 20 minutes is 4,200 liters, or the tank gained 4,200 liters of chemical in the first 20 minutes. Now look at this. C of t is liters per, what was it, minutes. dt represents the change in minutes, so it's kind of like you're multiplying by minutes. Well, if you do some unit analysis, if you do liters per minute times minutes, you would get liters, and that's exactly what the units are on your answer. Okie doke. Another way to illustrate the net change theorem is to examine the velocity of a particle moving along a straight line where s of t is a position at time t. Then the particle's velocity is v of t, which is the derivative of position. So the definite integral velocity from a to b is equal to the position at b minus the position at a, which is the displacement or the net change in position, which is not the same as the total distance traveled. Okay? So the definite integral of velocity represents the net change in position of the object or the displacement of the object. When calculating the total distance traveled by the particle, you must consider intervals where the velocity is negative and intervals where the velocity is positive. When the velocity is negative, the particle is moving to the left, so it's kind of backtracking. And when the velocity is positive, the particle moves to the right. So if you just integrate velocity, it won't take into account the fact that it backtracked, and it'll just give you how much it moved from where it started. Classic example I like to use is if you go from your house to the closest McDonald's, let's say it's 3 miles away, and you come back. If your displacement, your net change in position would actually be 0 because you stopped where you started. But your total distance traveled would be 6 miles, okay? So if you integrated your velocity over that time, you would actually get 0 because it gives you the definite integral of velocity gives you your change in position. So you would get 0 because your final position is right where you started. But if you want the total distance traveled, you'd have to figure out how much, you'd have to integrate your velocity over the time interval that you went out, and then over the time interval you came back, and you get 3 miles out, 3 miles back, you get a total of 6 miles. So at the end of the day, to get total distance traveled, you integrate the absolute value of velocity. So the displacement of the particle and the total distance traveled over a particle can be written as the displacement is equal to the definite integral of velocity, which is just S of A minus, or S of B minus S of A. How it would show up in this picture is you see you have positive velocities here, negative velocities here, and positive velocities here. So if you just integrate the velocity, it would count this one is positive, this one is negative, and this one is positive, and you would get the net change in position. The total distance traveled, you would integrate the absolute value of velocity, and what it would actually do is flip this region up to count it as positive. So you do A1, A2, and A3 all together, and that would be the total distance traveled. Okay, because remember, when your velocity is negative, like in this region, you're moving backwards. So it's like you move forward for a good bit here, then turned around and moved backwards, and then turned around and moved forward again. So you're backtracking a little bit, so your change in position is, or your displacement is not going to be the same as your total distance traveled. All right, so a particle is moving along a line, so its velocity is modeled by v of t, feet per second at time t. What's the displacement, and what's the total distance traveled? Now, I've graphed it here from 1 to 5, so you could see that there's some negative velocity here. Well, the displacement is just the definite integral of velocity. So you just integrate it, plug in 5 and 1, and subtract, and you would get 128 over 12, which is 32 thirds. So the particle moves 32 thirds feet to the right, which is like 10.666 feet to the right. Now, to find the total distance traveled, you need to calculate the definite integral from 1 to 5 of the absolute value. So if I go back and look at this graph, you can see that there are several places where the velocity is equal to 0. So what I need to do is set that function equal to 0, and we can factor it to determine that the velocity is positive from 1 to 4 and negative from 4 to 5. So I would integrate the function from 1 to 4 of v of t, and then integrate the opposite of the velocity from 4 to 5, because if you integrate from 4 to 5, your answer is going to end up being negative. So you want to subtract it so you take the opposite of it. So integrate from 1 to 4, plug in 4 and 1 and subtract, and then integrate from 4 to 5, plug in 4 and 5, subtract, and take the opposite of that, because from 4 to 5 you get negative 7/12 feet, which means you move 7/12 feet backwards, but you want to count it as positive because you're looking for the total distance traveled, and that would give you 71 over 6. 71 sixths feet, which is 11.833. So you can see that that is greater than the displacement, which was 10.667 feet, which makes sense because the velocity dips negative, so the displacement is, you're going to have some backtracking. The total distance traveled would take that into account. Okay, so that's the distinction between total distance traveled and displacement. All right, guys, that's it for this section. I know we covered a ton, so please reach out to me if you have any questions, and take care.